Um, so, by the way, one thing I also want to let you guys know, the last homework 4, will be announced, okay, later today, okay. That's about time. Yeah, so this is the last homework, and yeah. Because we only have like 2 weeks left, right? I mean, other than this today's lecture, like we have 2 additional lectures, and then it will be the final exam. Okay? And I think like following the final exam, like the next week will be like the programming exam. Okay, just like the WeChat. Okay. If you don't, I mean, do not know, okay, I also ask like, also ask the TA to raise like the points for the programming exam, okay, so that I mean, hopefully it can help you, you know, with the additional credit, okay. Okay, so back to the while we're waiting, okay. So now, okay, if you assign a value to each node, and we weight each edge like this, then the shortest path previous will be the shortest path, you know, after you weight after you weight the edges, or vice versa. The shortest path you obtain after you weigh the edge, okay, will be the shortest path in the original graph. Okay, this is perhaps more important because eventually what we are going to do is we are going to use the reweighted graph to compute the shortest the path, the shortest path. Okay, so we established this theorem already. Okay, that's like we discussed like you know, last lecture. Okay, so you know, so the short path from U to B after weighting, okay, will be the previous short path from U to B, the weighted path from U to B, okay, plus HU minus HU. Okay, and this is true, okay, you know, for every pair of U and B. Okay. So the idea is if we can find a function, okay, if we are able to find a function, okay, this h, okay, such that, okay, after we do the reweighting, every edge, their weight will be greater or equal to 0. Okay, after the reweighting. Then, obviously we could like just run a diagram, LB, okay, from each vertex, okay, of this reweighted graph to obtain the shortest path for all pairs, right? So the idea is we want to make sure this one, after reweighting, every age after reweighting is greater or equal to 0, right? So what is this? This means, HB minus HU is smaller or equal to WUB, right? Right? our related. Okay, related formula. If we want to make sure that WH will be greater or equal to 0, so this one has to be greater or equal to 0. Then you move like HU and HV to the other side. So you have this HV minus HU small equal to W U. So doesn't that look familiar? Doesn't that look familiar? Remember, in one of the discussion previously, we are talking about. Remember, we are talking about using like a shortest path, single source shortest path to solve like a special linear program. To solve linear program. Okay, in there, okay, each node is a variable. Each node represents a variable. Okay, and you have like a certain node minus another node, like a smaller equal to a value. Okay, we say like we call that what's that? The linear program of differences, right? I forgot like the exact full name, but I mean that was like in the previous slide. Okay, in the previous slide. Okay, not this one. Previous set of slides. We talk about something similar to this because like each of these basically represent a variable for you, a variable for me, a variable for you. Yeah? So we are interested in finding the assignment of V and U, okay, such that the difference is small or equal to a certain number. Yeah, this we already know how to do it. Okay. So we want to find a function, okay, h from V to R such that WH UV greater or equal to 0 for all possible UV, for all age, basically, for all age. Okay, and we know we can use building form, okay, to solve this difference constraint. Okay, the set of difference constraint. Yeah, that's like a full name for that. So, and we know like because we need to call the building form one time to find such assignment. So the time complexity is big O E. Okay, so once you find such assignment, as I said, you try to do like a graph reweighting, and the reweighted graph now has no negative weight ages. Okay, if it does not contain any negative weight ages, then you could call Dytron algorithm, to compute like single source shortest path. Okay, but you need to call it V times, right? Because you need to do it from every node. Because now we are interested in finding like all pair shortest path. Okay, so the Dytron algorithm time complexity is big O E plus D log D. Okay, so now because we call this D number of times, so time complexity becomes like DE plus D squared log D. Okay, so that's like we call Dytron D number of times. Okay, and then after you solve, you find like the delta H find the delta HUV. Okay, you find the delta HUV. Your delta will be the shortest path from U to V in the original graph will be your delta HUV minus HU plus HU, right? Just move these the other two terms to the left. And then, you just do that. To get your delta UV, okay, for every pair. Because you need to do this for every pair of nodes, so complexity will be big O V squared, because we are talking about every possible pairs, right? So, we have these three steps. The first one, solve the system of difference constraints, the equation, by using the Hilbert form. Okay, and the complexity is VE. The second one, the ground of the actual element, V number of times. The complexity is VE plus V squared log V. The third one, compute that show the paths for every pair that will be V squared. So consider all these three steps. The total time will be VE plus V squared log V. Because, after all, this complexity of the wrong index of V number of times only step 1, step 3. Okay, so this is the final complexity. So, we call this algorithm Johnson's algorithm, because it is found by this guy, William Johnson. Okay, actually, he's not really what should I say? He's not really trying to come up with any spectacular algorithm to do that. It's just he's trying to combine the existing algorithm, but he's doing this very intelligent, and he's able to reduce the time complexity. Okay. So think about this. We have three different approaches to do all pair shortest path. The first one result in V squared log V, right? The second one result in V squared. The third one is like this. Which one is the best? Well, it depends, because the age, if it's dense graph, the age is roughly V squared. If that's the case, this one, is going to become kind of like a V cube. If it's V cube, then it's similar to Floyd-Warshall, right? But when your graph is not dense, if your graph is not dense, this one indeed is a better algorithm, compared with Floyd-Warshall. Okay, because if the graph is not dense, your age, you don't have that many ages. Okay, then yes, this one the complexity is lower than this V cube. Okay, it's lower than V cube. Of course, for small graph, I would say Floyd-Warshall still runs faster for all pair shortest paths because it's simple. It does not involve additional lower order terms that much. But this one it actually involves many steps. It is more complicated. You will see a lot of lower order terms this one, like this one. So if the graph is small, then the Johnson's algorithm is not going to be as effective as Floyd-Warshall. But when your graph is big, and it is not dense. Okay, in these two assumptions, then yeah, the Johnson's algorithm, because the time complexity is better, so it scales better than Gold-Washington. Okay, so that's it for this part. So we finally finished like all the shortest path discussion. Okay. It is important. There are many occasions in graph theory, or like for a human graph, like you need to design algorithms to solve some problems. And the shortest path is like one of the most like representative problems in graph theory. Of course, previously we also discussed like Newton's spanning tree, right? So yeah, keep that in mind, okay? Because the next one is also going to involve like graph, but it's not that it's going to be a little bit complicated. So we are going to discuss Newman's curve. But honestly, I do not think we can finish this part today. I plan to cover only half of it. Okay? And the next time we will finish it. And hopefully also going to cover like a little bit of NP-complete. Because like it looks like if you cover like you got tissue LVs in class, like you have to every completeness is like something that you have to cover. So to be exact, okay, we actually have two different problems to consider. Okay, the first one is called flow networks. Okay, what we maximize the flow from the source to the destination. Okay. The second problem is called max flow mean cut. Okay, this is theory. Okay. So I guess today we're going to cover like the first half of the program. So to be exact, we are going to discuss what we call maximum flow. So what is a flow network? A flow network looks something like this. Okay, so it is obviously a graph, right? It is a graph. Okay, there are two important special nodes. Okay, the first one is called source node, where all the edges are outgoing edges from this node. Okay, so you can see that. Okay, that's like the two outgoing edges in this particular example. Another one we call it terminal, or another way to call it is sink. Okay, so it is represented in this graph as a heat Okay, so in this key, okay, the signal it is special in the sense that all the edge associated with this node are incoming edges. Okay, so for this signal, okay, so you could imagine, okay, it's kind of like water flow, right? Water flow. So you have the source of the water, right? So water always comes out from that place. Okay, so that we call that source, right? And that signal or that terminal node, okay, is where water goes into. Okay, like the sink in your kitchen. Okay, like 就是那个水槽里面那个水都会跑到最后面会跑的就是去那个地方。Okay. So these two nodes are special. Okay, and there are some additional things to say. Okay, first, okay, the edges are directional, yes. And each edge is associated with a weight. Okay, but this weight is a little bit special. First, we usually only consider integers. Okay, we usually only consider integers. Why do we consider integers? We will get to that later. Okay, the reason is because for algorithm to solve this maximal flow problem, okay, it will be easier, okay, if we only consider integer weight, okay. And the second, what exactly this weight represent? This weight represent the capacity. Okay, remember I talked about I told you okay, it's just like a water flow, right? Just like water flow. So you can imagine each edge is kind of like a pipeline, like a pipe, water pipe. Okay, you know water pipe has like a size, right? Bigger water pipe like can accommodate like a bigger flow, right? Smaller pipe, water pipe can only like a small amount of water can go through, right? So that integers stand for like the capacity of your water pipe. Of course, I mean, when I try to illustrate this flow level as like like a water pipe, or I try to use water to explain this, but it could be applied to many different fields. Okay, it's not just like for water. It could be used for like a network. It could be used for like traffic. Okay, a lot of things have like a similar flow network nature. Okay, it's not just for the water. Okay, so given a flow network, what we care the most is the maximum flow you could push from source to the terminal. So can someone tell me how much you can send from S to P in this graph? Just by intuition? Nobody? Huh? 多少？70. Nah, impossible. Think about that. Your signal, you can only calculate like 30 in total, right? 不可能70啊，因为10加20就是30，对，最多就是30，对不对？然后你这边也是，你搜索出来的就20加10，对，你最多是30。对，so it's impossible to be 70, right? Intuitively speaking. So it will be bounded by 30. So how much? Huh? Sense. Good guess. Good guess. Okay. Yeah. It's like this. Okay. You will find that. Okay. It may be a little bit more complicated than you. So, so the application for the program, as I said, it could be used for transportation. It could be used to display computer networks. Okay, just like the computer network, each connection, each link also has capacity. Okay, so that capacity can be considered as like the capacity of the flow in the flow network. And you can also consider the electrical distribution, like 电路学啊，电路学不是也有那种电子这样子，就是它的分布啊什么东西的。That is not my expertise. Okay, I will just stop there. But you guys have taken like电子电路，对，说电子电路 ，not too long ago, like supposedly. Okay, 你们大一还大二修？没有修过。你们现在没有修电子电路吗？没有。你们硬体的课程有哪些？好奇。啊？什么东西？数理性的，因为至少教电子也没有。数理性的老师教什么？啊？哦 ，VHD 啊。老师是谁？是陈谦老师。其实应该要一点点的，就是我当然知道说，OK，我们是自动系啊，但是因为这个跟课程没关系，如果做一下，我觉得说其实毕竟自电学院，我觉得有一些议题还是要讲一点。对啊，虽然说我不是我的领域当然不是议题啊，但是我觉得说完全管理还是不太行，因为我们出去外面大概可能有超过60%以上的。到时候会去硬体厂商，你们想到你们台积电做的多，台积电基本上还是硬体厂商，对，所以像什么联发科啊，那个卖干的地方也是硬体厂商，对，那其实你如果说对硬体懂一些的话，对你将来的投入的发展都有些帮助，都是后面再讲，下任主任希望他给我有余力吧，真的能够做这个事情就做这么多。Okay, and obviously, the flow network can be used for water distribution, right? Okay. So, and also, in the discussion that we just talked about for the flow network, it is very limited, right? In the sense that many of these applications, okay, we have like multiple sources and we have multiple sinks, right? 就像说这个交通嘛 and traffic, okay, obviously, okay, even if you only consider highway, okay, I mean every city has entrance to the highway. Every city has like an exit. Okay, so the entrance can be considered like the source, and the exit can be considered as a sink. Okay, so you have multiple sources and you have multiple sinks. Okay, so but in the flow network model, we only study one source and one sink. So it is very limited. Okay, but you will find that we will relax. If you consider flow network, the flow network can be easily extended to consider like multiple source or multiple sink. Okay. So yeah, we only consider like single source, single sink, but we could extend that. So we so this is important work. Not yet. Okay, but yeah, with the certain extension, we could cover that. So now we are talking about flow, right? We want to maximize the flow. Okay, but for the flow, when you inject the flow into this flow network, there are some stuff. I mean, we need to, some constraints, some rules. Okay, we need to remember. First, source node has no incoming flow. We know that. Second, terminal or sink node has no outgoing flow. Okay, that one we also know from what I mentioned about flow network, right? So this is not new thing. Okay, this is not new thing. But for all the other nodes, this is important. The internal nodes has net zero flow. So when you inject the flow into this network, okay, any node inside the network, okay, the incoming flow should be the same as outgoing flow. This is obvious, right? Think about that. If not, what happens? Yeah, if you use water as an example, okay, 我们都用水当个例子。如果你看到一个地方，只有水进来，没有水出去，什么事会发生？淹水嘛，对不对 ？You have like big issue, right? The flooding, right? No, the other way around， 只有水出去，进来的水不够，这有可能一直发生吗？你又不是变魔术，对不对？ You're not a magician, right? So the water doesn't come out nowhere, right? The water has to come out somewhere. But remember, this node is an intermediate node. Okay, it does not have the source. It is not the source of the water. So it does not, so the incoming water will be the only how should I say that? The only incoming water. There is only incoming water you could use. So the outgoing water and the incoming water should balance each other, right? Okay. I mean, for obvious reason. Okay. All units of flow going in must be going out. And we also know no edge is overcapacity. I mean, we shouldn't have an edge. Okay, and remember that we said the integer of an edge indicates the capacity. Or you can, I just told you that you can imagine that as like the size of your water pipe. I mean, if the pipe is this big, you couldn't inject more water into this pipe, otherwise pipe breaks, right? Okay. So the capacity, okay, no edge is over capacity. So under these rules, we want to be able to find the maximum flow that can be pushed through the the network. Okay, from the source to your sink. So, the first is about the location. Okay, S stands for the source. P stands for the sink. Okay, or terminal. Okay, and so we have like FUV. Okay, FUV stands for the flow on the edge from U to B. Okay. And the VU stands for the backflow on the edge from B to U. I mean, this may sound confusing, but please bear with me. Okay, please bear with me. Why do we need to model the backflow? Why do we need to model the backflow? It will become more obvious later. Okay, so we have first FUV stands for the flow edge from U to B, and for the same edge. Remember, the edges are directional, right? The edges are directional. So I mean, so FUV, that means that we have a directional edge from U to B. Okay, that's why you have FUV, and also this FUV must be smaller than the capacity, right? The capacity of this edge. According to the rules that we just discussed earlier, right? And then the FBU will also assign something that is going back from B back to U, where it is in the opposite direction of the direction of the edge. Okay, of the direction of the edge. This is the illustration. And the CUV stands for the capacity of the edge from U to B. So, as I say, the FUV is going to be smaller or equal to CUV. And the CFU, what is CFU? CFU is a residual capacity on the edge from U to B. So, for example, okay, say that your capacity is 30, and now you push 20 units of water through this pipe, then your CFUV will be 10. Okay? So this is like, hopefully it's not like difficult to understand. Right? Just the remaining capacity, right? The remaining capacity. And the GF is the graph where the edges width are the residual capacity. So in the GF, we only consider CF. We only consider CF, basically. So this notation, okay, is used, okay, for our flow network, okay, for the Elwood discussion. And the GFUV, by the way, GFUV is the graph we actually use when we run the Elwood. Obviously, initially, when there's no flow, the GF equal to G, right? GF equal to the original flow network. But after you assign flows, I mean, some capacity will be used, right? So you only have some remaining capacity, so it becomes like GF. Okay. So this is the notation we are going to use. So let's take a break and come back to our discussion.